Our brains work much better when they have something graphical, okay, a geometrical pattern.
What for what?
That's a really good question. The topic of today, we have to introduce it, and it's equipotential lines. And it's a super powerful tool here in physics. From the Latin, okay, from equi, equal, and potential. That came from the word potential field that we are covering today. If we pick this equation here from the potential of a point charge, we can see, if we work in polar coordinates, it's even easier, that is a full symmetric one, okay? In 360. If we define the equipotential lines like all the points that have an equal value for the potential line, of course, has to be a circle. In the 3D space, it's gonna be a surface. So you can call it also equipotential surfaces. The equipotential lines are always perpendicular to the field lines. Important note to say is that these equipotential lines only exist for conservative fields. For example, we started with the electrostatic field, but if you move to his cousin, the magnetostatic field, we can see that it's not a conservative field by definition. So you can't find a scalar field that compresses somehow all the information of a vector field.
What do you mean by that? Can you give me an insight?
Yeah, sure. Let's go for the intuition of an equipotential line or surface. Basically, it's giving us all the points that has the same potential, right? So it's giving us a way to move a charge, in this case, through that surface or that line for free, with no energy applied. That's amazing, right? Moreover, one of the laws of electric fields and conductors is that the electric field has to be perpendicular to the surface of this conductor, and also that the difference in voltage from two different points of the surface has to be zero. Moreover, this means, by definition, that the surface indeed has to be an equipotential surface. And you can then substitute it by a particle like with the same charge in it. Indeed, this means that if we connect two surfaces through a wire, the potential will be distributed, okay, the voltage, if you prefer. If you connect the wire to the earth, that is a good conductor, and this is called grounding. So now we are gonna learn how to actually draw the equipotential lines, because they are pictures. So this was really useful for Maxwell.
Who is Maxwell? This guy?
Oh my goodness, yeah, it's that guy. Anyways, how are we gonna actually draw these lines? So first of all, we are gonna give you an example, okay? The positive will act, their field lines, like a source going outwards. The drain is gonna be the negative, so the field lines are gonna be inwards. And then the equipotential lines, by definition, has to be perpendicular, okay, in every part of every field line, and they can never cross, of course. So, as you can see, here they are always perpendicular, and here in the middle also. Amazing, right? Other application that can be really interesting for us is our own hearts. Why? Because they are basically electrical surfaces, so we can measure using these equipotential lines, right? And then we can know, depending on the bits per second, if they are normal, hard, or if not, if we have to visit our physician. But this is not the end of the story, guys. It's only the starting point. For example, gravitational fields. They are also conservative. We don't have to give more energy to maintain the satellites there. So, the orbit where the satellite is by definition an equipotential line. It's something more, from our days. It's the case of a map. For example, if you take these two maps, in this one, the lines are much more closer to each other. They are equipotential lines, and they are measuring the heights, okay? So, this is giving you that insight that the inclinations are much higher here than here. And the most interesting thing, we are given a 3D feature in a 2D Euclidean map. Amazing, right? So finally, we have covered one of the most powerful tools that we have here in electromagnetism, and James Clerk Maxwell used to use here at King's College London as one of the pioneers of this field. Thanks.